All right, we're going to formalize some of our vector components here and look at them in what's called component form instead of just trying to figure it out by scale drawings. So we're going to look at them in terms of a coordinate plane. We're going to formalize things in terms of something called unit vectors and how we can kind of easily combine vectors without having to rely on a lot of kind of just geometric sketches. All right, so we're going to talk through these different pieces of what component form is. We're going to talk about our unit vectors and then linear combinations of those unit vectors. All right, so the kind of key idea here is if I have 2 points, right, I have point A and point B, I can define that vector A to B. So again, going from A to B is different than going from B to A. It's just A over and up. And so this is very similar to how you've determined slope before, right? I'm going to take my y values, y2 minus y1, and then x2 minus x1. That's going to give me components, right? An x component and a y component. And we write that here with these angle brackets. So if we were to take 2 points, so if point A was 3, 2, and point B was let's say 5, 5, right? Those are points in a coordinate plane. If I'm looking at the vector AB, so going from A to B, that is going to equal, as a component, I'm going to subtract my x values, so 5 minus 3, and then I'm going to subtract my y values, 5 minus 2, and then I will get, as an end result, the vector 2, 3. Right? If we think about what that's saying here, if I was to take my coordinates and actually graph them. So if I was to go over 3 and up 2, 1, 2, 3, up 2, there's point A, and then point B is over 5, 5 and up 1, 2, 5. There's point B. That vector is what we just determined. And really what we're looking at is adding up a component. I've gone over 2, and then I've gone up 3, and those are exactly what I have in my component form down here. So it's just another way to think about this as we put it on a coordinate plane and use our properties of ordered pairs. All right, so this example again is kind of what we just went through. All we need to take care of is that if we're going from A to B, the order is important. So if we're going from A to B, right, my A values are going to be x1 and y1, and then my B values are going to be x2 and y2, and we just want to make sure that we go in the correct form of x2 minus x1. So if we do that and subtract them, what we'll find out is that that is our final value. So that piece here, 0, 6, is our component form of that vector if I go from A to B. All right, so you're going to try this one out. Again, you're going from A to B. You're going to label x1, x2, y1, and y2, and then do the appropriate subtraction and write your final result in component form. Okay, if we apply this a little bit more, we have what's called our magnitude of our vector, and it's written, it looks like absolute value, but it's basically the length of our vector. If we look at this, all this really is our distance formula. All right, so I have the distance from A to B. That length is our magnitude. So we just apply the distance formula. If you want to think about it as Pythagorean theorem, a squared, b squared, c squared, you can do that. That's how it works to get our distance formula anyway. So we're going to take that idea and be able to apply it to find the magnitude of a vector. All right, so again, same idea. We have A and B. We need to make sure that A, since it came first, becomes x1, y1, and then B becomes x2, y2. We drop those values in, we plug it into a distance formula, and then when we simplify, we get a value of 6. There's our value. Okay, so you're going to pause at this point, and you're going to find the magnitude of that vector. And again, it's just an application of our distance formula for those two coordinates. All right, so what we have for some operations on vectors is we can add 2 vectors, all right, we can subtract 2 vectors, and then we can multiply by a scalar value. If they're in component forms, it's really pretty simple to do. So all this is looking at is if I have vector A, so if A is 3, 1, and then B is 2, 5. If I want to add up A plus B, all I need to do is look at their components and add them together. So what I can see is if I was to use the diagram from above, this is A1, A2, this is B1, B2, and to add them together, I just get 3 plus 2, and then I get 1 plus 5. And that'll simplify to go from there. Subtraction works the same way. And then our final kind of scalar multiplication is if I have a value in front, I just can multiply it times my components to get my values. So again, we have 2 vectors in this case. Well, 3 vectors in this case, sorry. We're finding 2w plus y, right? Again, since it's already in component form, it's easy to solve. We just look at the matching components and do the operation. In this case, we have a scalar operation, and then we have an addition. And the same order of operations are going to hold, where I'm going to have my scalar multiplication first, and then I'm going to add. So when we do that, we have our scalar multiplication, right? The 2 distributes through, and then we can now add our like terms. And so we can see that at the end, 4 plus 2 is 6, negative 10 plus 0 is negative 10, and that's it. That's our operation with those in component form. Same thing for B. All right, we work through our operations. Now I'm looking at not just y, but I'm scaling z by a negative value and then subtracting. All right, so again, I rewrite it, and I have my addition. I have my scalar values. I push them through. All right, so negative 2 times negative 1 is 2, negative 2 times negative 4 is 8, and then I just add like components, and I get 8, 8 as I'm doing my vector addition. All right, so given those vectors, you need to determine 3v plus 2w. Just take care to make sure that you do your scalar multiplication before you do any addition. All right. Our next idea is this idea of what's called a unit vector. So a unit vector is a vector that has a length of 1. All right. So we can always determine a unit vector by scaling it by its magnitude. So if a vector was had a length of 5, so a magnitude of 5, if we were to find those components, right? So we figure out the x, the over, and the up, and divide everything by 5, we would basically be scaling this back down to be a length of 1. And that length of 1 would be our unit vector. So dividing by the magnitude kind of makes sense. It would be dividing all the components by the magnitude would give you a length of 1. We have some standard unit vectors that we want to understand. The first is a length of 1 along the x-axis that we call I, and a length of 1 along the y-axis that we call j. And so for this one, for I, right, if I just go out in component form, so for component form for I know that I'm going out 1 in the x value and 0 in the y value. And then for j, I'm going 0 in the x and 1 in the y value. If I was to do the length of that, that's obviously going to have a length of 1. Now what we can see is that we can use multiples of I and j to determine and create our any vector that we want. The way that we do that is we take a vector, so let's say a and b, we can break that apart into a, 0, and then 0b, and then we can factor out, all right, that scalar value of b and a. And then this is defined as I, that's defined as j. So we can take this vector and write it as a linear combination of I and j. So this is again making a general unit vector. So I have a vector that goes from 4, -2. And to determine the unit vector that's in the same direction, all right, I'm going to find the magnitude of this, and then I'm going to divide by that. So the idea is this is my vector, 4, -2. To find the magnitude, I just do the first component squared plus the second component squared, take the square root, right, which gives me 1 over root 20. I scale my vector by that value. All right, so I'm going to push this radical through to both of my values, and that will give me a unit vector in the same direction as for -2. And if we think about what that looks like, if I had my coordinate plane, right, 4, -2, 1, 2, 3, 4, -2, that's my terminal point. My vector looks like this. That has a distance of root 20, and what I'm defining is a unit vector that would have a length of 1 that's in the same direction. That's what we're doing algebraically. All right. And if we push that through, we get our kind of simplified value, and then we rationalize and go from there. We could check that to make sure that it has a magnitude of 1, just by again taking this value squared plus this value squared, and the square root of that whole thing would give you 1. All right. And then that's exactly what they do here. They take your component squared, 4/5 plus 1/5 is 5/5, which is 1. The square root of 1 is 1, which we knew it had to be because it's a unit vector the way that we defined it. All right, so you need to find a unit vector in the same direction as 5, -3. You're going to need to figure out the magnitude of that vector, and then you're going to do 1 over the magnitude, scale your vector by that value, and you'll get a unit vector. Okay, so what we're looking at now is how do we take our values and figure out what they are in terms of I and j. Again, we remember that I is along the x-axis and j is 1 along the y-axis. So the way we're going to do is, if we think about what this is actually looking like as a graph, and I sketch where these things are. So if I go -3, -3, 1, 2, 3, that's point D. And if I go to E, which is 2, 6, 1, 2, 1, 2, 3, 4, 5, 6, there's point E. My vector starts at D and goes to E. Right? If I want to figure out where this goes in terms of over and up, I know that it goes over and up some amount. And that gives me that resultant vector. All right. If I want to know how much over and how much up, I can subtract my x coordinates. So if I take, in this case, 2, right, minus the 3 that I had here, that is a distance of 5. If I do the same thing for my y components, I'm down 3 down here, and I'm going to go up to 6. That's a distance of 9. What we can do now is take our tiny little unit vectors, so the distance of 1, and apply them across. So if I go 1, 2, 3, 4, 5, that gets me to be a 5. A way that we can write this is I take 5 times I is in that direction. Same idea for going on up. If we were to take our values for here and add j 9 times, what we'd see is that that value becomes 9j. Where j is that unit vector that's up. So our whole thing, if I was to take this value, becomes 5i plus 9j. And those are my component forms in terms of those unit vectors. So that's what it's going to look like here. It's going to go through and do our subtraction, what we just figured out. And then I subtract, and then I have 5 and 9 in component form. If I want to translate that into unit vectors, it's pretty simple. I just have my value 5 becomes my I, 9 becomes my j. Alright, so you're going to try this one. Again, you can draw a sketch if it helps you, but you're going to find your vector in terms of I and j, again where I is the unit vector along the x-axis and j is the unit vector along the y-axis. Okay. Another way that we can look at vectors is in terms of components, and this just goes back to our triangles. So if I have a vector, what I can do is I could figure if I know the values in terms of an angle, right? Then what I could do is I could use sine and cosine to figure out my components. And then I can use those times a unit vector to figure it out. So if I had a vector that was a magnitude, let's say, of 10, and the angle that it forms is, let's just say, 25 degrees. What I want to do is I want to figure out those components, both in the x and the y direction. I didn't do that very well. X and y, those always form a 90-degree angle. And so I can see here that what I'm going to have is this value is going to be 10 cosine of 25, and then the up is going to be 10 sine of 25. That's just some number. Okay, so this piece, that magnitude, is my 10 cosine of my angle, and let's say that that number, whatever it is, if I remember that I can drop those little unit vectors along here, that value, whatever, how many fit in there, those are my values of I. I'm going to take that and scale it. So my final piece, right, if I was to do this in terms of I, is 10 cosine of 25 times the unit vector I. And this is 10 sine 25 times the unit vector of j. If I add those two together, then I get my final vector, right, which is the component there. So that's all it's looking at. That's what this up here and what this diagram is showing you. It just breaks back down into your right triangle trig. Okay. So if we were given something with a magnitude of 7 and a direction angle of 60, we can just put those values in, and I get from here my angle, my magnitude. I do some simplification. This would be 7/2 I. This is 7√3/2j. And we can then combine those if we need to into a linear combination of our unit vectors. But this is our final vector value. Right? So if it helps to draw a picture, you can, or you can just use the equation that's provided here. And then we could check it with our geometry, but we don't need to. All right. So you are going to find the component form of vector v, given that it has a magnitude of 12 and a direction angle of 300 degrees. So you're going to use that form that we just looked at to be able to put it in component form. All right. Last piece is if I was to need to figure out an angle. Again, this is just going to fall back on our triangles, right? So our use of trigonometry. If we think about what this vector means here, so vector p means that I have some vector, I go over 2, and I go up 1, 2, 3. Let me redo this. I go over 2, and then I go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my terminal point, and then my vector goes along there. If I'm looking for that angle, right, the direction angle, basically I just need to figure out, if I look at my triangle, this and this is a 2, this is a 9, this is the angle I'm interested in. Just by using my trig, right, that's my opposite, so I know that tangent of theta is 9/2. If I want to figure out what theta is, I take a tangent inverse, which is right there, and it gives me a final value that I can use. So that becomes my direction angle. If I needed to translate that somehow, so let's say I needed like a bearing angle, if I'm looking for that from the north, right, I can still use my theta value. I could do 90 minus theta to figure out that direction angle. However, I need to express it for the problem. But again, you're just using an inverse value with your trigonometry to determine your angle if you know the component form of your vector. And there's your picture that we just drew. All right. And that's it. Good luck.